So we saw already what is a linear least square solution, okay, or what is called LLS, linear least square solution, and right, which we saw turned out to be x hat is equal to A transpose A inverse, okay, A transpose Y, okay. And in order to relate it to, let's say, a deblurring problem, right, you can think of A as your blur matrix. We have Y is equal to, right, hx plus n, and because of those noise, right, it takes you away from the span of, so Y is no longer in the span of the columns of H, and therefore, right, one would then want to ask for a solution X, okay, such that the norm of Y minus Hx square, norm Y minus Hx square is as small as possible, in which case your right, X hat, right, will then turn out to be H transpose H whole inverse H transpose Y. Okay, that is one way to sort of see how this least square solution will be useful for kind of a deblurring problem. Okay, but then right, such a solution is not really the most right, elegant one to arrive at. We'll see how to incorporate prior and so on. But then, right, I just wanted to indicate that if you have an observation for which a solution does not exist, then what one could do is to solve for a linear least square solution. Now, the second condition of Hadamard, if you recollect, that was about uniqueness. Right, uniqueness in the sense that if a solution exists, it ought to be unique, right, is what it had said. Now, what if you had a situation where, let's say, Y is equal to AX and or let's say at AX equal to Y, whichever way you want to write it, let's say AX equal to Y, and you want to solve for X, where this is again, let's say, M cross N, this is M cross 1, and this is M cross 1. What if let's say M is less than N? Okay, so you have an underdetermined system of equations, and we know that right, when you have a situation like that, you could end up right, you could have multiple solutions for a given Y, multiple solutions for a given Y, right? That means there could be multiple x's, right, which will all work to kind of right, give you the same Y. In such a case, one can, of course, one can now say, okay, well, in which case I cannot solve this problem because there is no unique x. Although I know that a solution exists, but then right, there's no unique x that will take me to that Y. Okay, there are so many x's, which one to pick? So what one could do is one could look for an L1 norm or for x. Okay, so you could kind of look for that x, okay, which has the smallest L1 norm. Okay, this is something like sparsity and so on, which is useful in compressive sensing kind of application. But the more easy thing to ask is what is called the min norm solution. The min norm solution. That means find that x, right, among all the x's that satisfy Ax equal to Y. Find the one that has the smallest norm. Okay, this should be smallest. That x which has the smallest norm. Okay, it's called really the min norm solution. Formally to kind of write this up, right, what you can say is you can look off, okay, so you can say that this is equal to saying that minimize, okay, so min norm solution looks like this, minimize norm x squared, because we want this to be minimum subject to the condition that subject to Ax equal to Y. Okay, because in this case we can satisfy this inequality, okay, not inequality but inequality, right, because you know that a solution exists, therefore among the x's we want to pick the one that has the smallest norm such that when A acts on it, it gives you Y exactly. Okay, not like the least square solution where Ax was equal to some Y hat, it was not equal to Y. In this case, Ax will be equal to Y. Okay, now frame it in a kind of with respect using a Lagrange multiplier. Then what you get is you can write this as J of x equal to x transpose x plus a Lagrange multiplier, right, which you can use here, which is be like lambda transpose Ax minus Y. So the whole thing boils down to using Lagrange multipliers. It becomes like this. Now we can look at dou j by dou x. That in this case will be 2x plus say Y transpose Ax, or lambda transpose Ax is A transpose lambda, right? As I already said. Even third term, of course, it doesn't even involve volume of all x. Therefore, right, you get this as 0. Or what you can say is 2x equal to minus A transpose lambda, right? 2x equal to minus A transpose lambda. Now, if you try dou j by dou lambda, that will give you simply Ax minus Y equals 0, right? Because that will only act on this term, that will give Ax minus Y equal to 0. Or in other words, Ax equal to Y Now if you substitute for x from this equation 1, then you'll get A into x is half minus A transpose lambda. Okay, that is x, right? From equation 1, this is equal to y. Or you can say minus A transpose lambda is equal to 2y. Or, in other words, lambda is, you can say, minus 2 A transpose. Okay, lambda is, of course, a vector here. Okay, please remember, lambda is a vector, so it can only, so it's multiplying A transpose multiplying the vector from the left. Therefore, you have A transpose inverse, okay, minus 2A transpose inverse y. Now, if this is the optimal lambda, put that in here to get your optimal x hat. Therefore, you get 2x hat is equal to minus A transpose times minus A transpose times 2x hat is equal to minus A transpose times lambda. So lambda is minus 2 into A transpose the whole inverse y. And this 2 and 2 will cancel off, this minus and minus will cancel off. Therefore, it turns out that x hat is equal to A transpose into A transpose the whole inverse y. Therefore, clearly, if you operate, okay, so basically this is your min-norm solution. Okay, this is your min-norm solution for x. For x, clearly, if you operate A on this x, on this estimate of x, let's operate. So Ax hat, if you do, you get A into x hat itself, as you found here was A transpose the whole inverse into A transpose the whole inverse into y. But A transpose inverse is equal to identity, therefore this is equal to y, right? Therefore this x hat does satisfy this condition that Ax should be equal to y, right? So the solution does exist, and then among the solutions, because there are multiple number of them, we are picking the one that has the smallest norm, right? Therefore your min-norm solution is really this. Now, okay, now if it so happens that, let's say, x hat is rank deficient, if A is rank deficient, that is, A transpose is not invertible, then one can compute the pseudo-inverse. And one can compute the pseudo-inverse of A using SVD. Okay, we've already seen what this SVD is like, so you can compute the pseudo-inverse of A using SVD, which means that given your A, which is M cross N, you can split it up as matrix U, which is M cross M, sigma U sigma, which is M cross N, V transpose, which is N cross N. Therefore, A pseudo-inverse, it's typically indicated as A plus. So A plus will be N cross M. This will be equal to V sigma plus, which will be N cross M, and then U transpose, which would be, so this is N cross N, this is N cross M, where let's just write down, right, what we mean by sigma plus and so on. Where sigma plus, okay, of I comma I is equal to 1 by sigma of I comma I. Look at this sigma of I comma I. If sigma I comma I is not 0, else 0 otherwise. Okay, and that would kind of give you the pseudo-inverse of A, and if you operate this A plus, okay, and if you apply this A plus, so your x hat, the min-norm solution, will simply be A plus y, okay, A plus acting on y. It's where your y is the observation. Now this is, of course, provided A is, if A was deficient in rank. Okay, if not, of course, if not, then you can directly do A transpose inverse, and then you'll get a min-norm solution. This is also min-norm, by the way. It is also min-norm solution, and the same A inverse. Let me also mention that that now if you go back to your least square solution, right, we had A transpose A, and if A transpose, okay, now you can even use this result for, okay, the min norm solution, okay, the min norm result, the pseudo inverse result for min norm can also be used for least squares. Can also be used for least squares when the columns of A are not linearly independent. Okay, what this means is that is A transpose A is not invertible in least squares. A transpose A is not invertible in least squares. Okay, if this happens, okay, then it means that the columns of A are not linearly independent. Then it means that if you try to do a least squares, then there is not just one x, there are several x's, right, that can kind of give you an x hat, which when acted upon by A will give you ax hat, which is equal to y hat, and that y hat will be as close as possible to y in the orthogonal sense. So that is the error between y and y hat is going to be small. Okay, but then, right, among the x's that will take you there, if you use the min norm idea, or if you use a pseudo inverse, then it will give you the x that has the smallest norm. Because A transpose A is not invertible. Of A are not linearly, when the columns of A are not linearly, that is A transpose A is not invertible. So, right, so the solution, the min norm. So such a solution is called min norm least square solution. Solution is then given by a pseudo inverse y. Okay, so it's called the min norm least squares. Okay, got min norm least squares. Okay, so this is if A transpose A is not really invertible. Okay, now these two conditions are over, right? As far as we can see. Now, what about Hadamart's third condition, right? Now, again, min norm is just one way out. I mean, if uniqueness is an issue, least square solution is one way out. If, let's say, existence is an issue, and suppose, right, somebody told you that let's say I have an operator, or I have a matrix that is both that is both 1 to 1 and 1 to, in which case, right, you have an A which is actually invertible. But we still feel that Hadamard had something else to say, which was his condition number 3. So coming to condition number 3 of Hadamard, right, what he said was the dependence of solution, right, should the solution should depend continuously. Solution F should depend continuously on the observation G. Should depend continuously on G. Now, this is what actually plays a very, very important role. Like I said before, if G1, right, is for G1 you get a solution F1 because of the fact that it's 1 to 1 it's invertible, A is invertible, and G2 gives you F2. If G1 and G2 are very close, then F1 and F2 we will ideally want them to be very close, right? Whether they're close or not depends upon the stability of the problem, right? So we want to examine the numerical stability of the matrix A. Numerical stability, let me write stability fully. So we are interested in examining what we call is the numerical stability of matrix A. So you are trying to solve Ax equal to y, okay, and we are saying that y1, okay, if I have y1, then my solution is A inverse y1, okay, which is x1. And if I give y2, then my solution is A inverse y2, which is x2. And we are saying that if y1 and y2 are very close, I expect x1 and x2 to be very close. But will they turn out to be close or not depends upon the numerical stability of A. Okay, so we would like to examine this notion in more detail. Okay, and right, in order to understand that, we have to talk about norm of an operator and so on, which is what we will see next. Let's first talk about a bounded linear operator, right, and then we'll continuously come down to the matrix. Okay, let's first talk about the general notion of a bounded linear operator. Okay, a linear operator L is said to be bounded if there exists a real number C greater than or equal to 0 such that for all x belonging to the domain of L, norm Lx is less than or equal to C times norm x. Okay, this is the domain of L. This implies that C is greater than or equal to norm Lx by norm x. The smallest possible C, right? The smallest possible C. So the smallest possible C that satisfies this condition is called the norm of the smallest possible C is the supremum of the RHS of 2. Let's say equation 2, because this is 2, taken over DFL minus the 0 vector, right? Because since we are dividing by norm x, and this smallest value is called the norm of L. Norm of L, and is denoted by norm L by norm L. Okay, that is norm of L is equal to supremum over all x belong to the domain of L, x not equal to 0 of the quantity which is given as norm Lx by norm x. Now, right, when we write supremum, okay, we should understand that supremum is not the same as maximum, right? It's a slightly more kind of a general idea. Okay, so what do we mean by, for those of you, right, who are wondering what supremum is, or what is called the least upper bound? It's called the least upper bound. Okay, so this is simply an aside, okay, for those of you. So given, for example, given a set E, its supremum is defined as A is equal to sup of E, where A is the smallest number such that A is greater than or equal to x for all x in E, for all x belonging to E. Important to note, the important thing to note is that A is called the LUB or supremum or whatever, least upper bound, and A need not belong to set E. Right? Whereas whenever you talk about maximum, it comes from the set. When you say maximum of the set, then you actually pick a number that actually belongs to that set. Whereas when you talk about supremum, right, it doesn't even have to belong to that set. For example, if you take E to be, let's close it from the left and open it from the right, okay, then the sup of E, right, is equal to 1, and you see that 1 is not in the set E. But then we know that 1 is the smallest number that is greater than or equal to all numbers in the set E. But then set E, okay, doesn't include 1 by itself because this is an open interval. Okay, that is the notion of the supremum. Now, using this notion, right, we would like to understand how to now talk about the norm of a matrix, because this is a definition for norm of a linear operator, and therefore, right, one would like to use this kind of a definition in order to be able to talk about the norm of a matrix. Okay.